In this video, I want to take a look again at finding maximums and minimums, but this time when you have some kind of constraint. Remember back in Calc 1, we did problems like this, where you're finding maximums and minimums. But then there was a set of problems that you said, don't just find maximum and minimums anywhere, find them on this interval, right? So you'd have a smallest x value you're interested in and a biggest x value you're interested in. And the way you found the maximums and minimums was you first looked for critical points, right? You took the derivative, set it equal to 0, and you found the places where that happened, and then you checked the endpoints, right? Because there's a theorem that said a continuous function defined on a closed interval, finite length, closed interval, has to have a maximum or a minimum. And we just figured that if it was the maximum or minimums happened inside, then Fermat's theorem said it had to be at a critical point. And so if it wasn't at a critical point, then it must be at the endpoints. And sure enough, sometimes you found maximums and minimums at the endpoints. Right? Now with more than one variable, so with two variables, we're going to say in the plane, you've got a region. Maybe it's a circle, maybe it's a square. You've got some region in the plane that your function is defined, and you want to say just on that region, what's the highest the function gets and what's the lowest the function gets. Maybe outside the region it gets higher or lower, but you don't care, just in this region. Okay, so it's more than just an interval now, it's going to be some region of the plane. And the theorem says that, right here, a continuous function has to be continuous, no breaks or anything weird going on like that. A continuous function on a closed and bounded set D in the plane must attain an absolute maximum value and an absolute minimum value somewhere on D. Now, the word closed and bounded, I got to make sure we understand what that means. Closed means it contains all of its boundary points. Right? So remember, a boundary point was a point where any circular disk around that point would contain some points in your set and some points out of your set. Every single disk would have to be that, no matter how small. You get some points in and some points out. That's the boundary. So the set D must contain all of its boundary points. To say that it's bounded doesn't mean that it has a boundary. It means that it's not infinite. It doesn't head off to infinity in any direction. That is, you could take a big circle and stick it around all of it, and D would be contained inside that circle, a circle of finite radius. Right? So this is not infinite in extent. You might say it has finite area. That's fine. So closed contains its boundary. Bounded doesn't head off to infinity. If that's the case, then your function, your continuous function, must have an absolute max and an absolute min. And again, we've got a Fermat's theorem saying that if those maximums and minimums happen on the interior, they have to be critical points. So partial derivatives equaling 0, or maybe the partial derivative is undefined. But then that maximums and minimums might be on the boundary, right? And if they're on the boundary, then you have no idea what the partial derivatives are. For instance, is the state of Connecticut. The highest point in the state of Connecticut is on the side of a hill. The side of a hill, not the top of the hill, the side of the hill. And that's because the top of the hill is in Massachusetts. And as you're going up the hill to get to the top, you start off in Connecticut, and you get to the point where the state line crosses, and that point where the state line crosses on the hillside is the highest point in the state of Connecticut. It happens on the boundary. The highest point in the state of Tennessee also happens on the boundary, but it happens to be at a mountaintop, shared with North Carolina, I think. But there's a higher point in North Carolina, but that is the highest point in Tennessee, right on the boundary. Nebraska comes real close to having its boundary, its highest point on the corner, but it isn't. But it's within spitting distance. You can see the corner point from the high point out in the middle of the plain. It's pretty flat, Nebraska. But anyway, we need to find maximums and minimums. And so here's what we're going to do. To find maximums and minimums, we're going to look for critical points on the interior, and then we're going to see what values on the boundary might be highs and lows. Okay, and that working with the boundary becomes somewhat problematic, and we will have more to say about that in the next video, which will be coming out next week. So I'm going to use the same example that we've used for the last couple of videos. Here's this function. I saw that, it had a local max and a local min, a couple saddle points. And the region that I looked at, just sort of randomly picked a region, was from -5 to 5 in the x direction and -5 to 5 in the y direction. So I'm going to say that's my region. That's the region I'm interested in. Yes, the function is defined outside of that region as well, but for just now I'm interested in the square where x is between -5 and 5 and where y is between -5 and 5. And I want to know on that region, what's the highest point? What's the lowest point? What's the highest function value? What's the lowest function value? Well, we did the work already to see, took the partial derivative, set it equal to 0, that on the interior, there were 4 critical points. 3, 2, 3, -2, -3, -2, -3, +2, right? Those are my 4 critical points. So now I need to check the boundary. What's going on the boundary? And you can see that the function on the boundary goes, up and down and up and down, and there seems to be a high point here, maybe, kind of high right there on the corner too. A little bit of a high point there, really a low point down there. Can't really see it. Or maybe you can kind of just barely see through. It's see-through here. It's kind of low down there, comes back up. So there's a bunch of ups and downs on the edge. And the question is, what's the highest one and what's the lowest one? Now, dealing with the boundary is tricky. You got to do different things depending on what the shape of the boundary is. In this case, the shape of my boundary is 4 line segments, right? And so I'm going to think of that as 4 line segments. I'm going to do it top edge, bottom edge, right edge, left edge, right? And see on each of those edges what's the max and the min. So the top edge is when y equals 5. So if I plug 5 in for y to that function, it now becomes just a function of x. Now this is a Calc 1 problem. Can you find where that function of x is maximized and minimized? Well, sure. Take a derivative. Set it equal to 0. Check the endpoints. Right? Now, I want to mention there are endpoints here at -5 and +5. Right? So if I do this, I take the derivative of this thing, I set it equal to 0, and then solve for x, I would find that x is plus or minus 3. Right? So that gives me 2 interesting points at 3, 5 and -3, 5. So on the graph here, that would be up here. At 3, 5 would be a point on the edge there, and at -3, 5 would be this one here. Right? So on that edge, there's a local high and a local low, right, that are candidates for being the absolute high and the absolute low on the whole region. So those are interesting points to me. There's also the endpoints, but the endpoints are the corners of the region, which I'll deal with all separately. Right? So my top edge had 2 interesting points and then the 2 endpoints. The bottom edge is when y equals -5. So plug -5 in for y, and now I have just a function of x. This is a Calc 1 problem now. Maximize and minimize this. Take the derivative with respect to x, and I didn't even multiply this all out. It doesn't matter, just like up there. It's a constant. Take the derivative at 0. So I get the derivative is -3x squared plus 27. Set that equal to 0 to find out when it's critical, and you get x is plus or minus 3 again. Same problem as up above, right? So this gives me 2 more interesting points, 3, -5, and -3, -5. And of course the endpoints. I'm going to deal with all those endpoints in the end. I should point out that as I work on these edges, if I had come up with the values of x here were 3 and 17, right? So that would be 2 interesting points, 3, -5, and 17, -5. I can say, wait, I don't care about the 17 because it's not in the region that I'm working on, right? The region I'm working on has x between -5 and 5. So anything out of that region, I would just ignore. In this case, both of the interesting points here are in the region I'm looking at. I'm looking at x between -5 and 5. So 3 and -3 are both in that range, and so I have to look at both of those. Then looking at the right edge, The right edge is when x equals 5. Y is between minus 5 and 5. Plug in the x equals 5, and now it's just a function of y. And so uh, I have this thing with a 5 plugged in for x. And again, this will be some number, but I don't care what number it is, and this will be a number because it's all just a number. When I'm taking the derivative, that's going to go to 0. Take the derivative, it's this, set it equal to 0, solve for y, and you get y equals plus or minus 2. So there's two more interesting points, 5, 2, and 5, negative 2. Right, this is on the right edge. This is over here. 5, 2 is in there. 5, negative 2 is that down in there. Maxes and mins on the edge, but not necessarily for the whole thing, but maybe for the whole thing. And then the left edge is with x equals negative 5. Do the same thing, plug the negative 5 in. This should be a negative 5. It looks like I was plugging in negative 5, but I didn't have it written as negative 5 here. So take the derivative of this now with respect to y, and we get this. This is critical when that's equal to 0, and you can solve for y to get y as plus or minus 2, again, giving me two more interesting points and the endpoints. Okay, those endpoints each time are just the corners of the region from minus 5 to minus 5 in both the x and y directions. So together, I have got a bunch of interesting points, a bunch of candidates for being the max and mins globally. Right? I'll move over a little bit here. There were 4 critical points on the interior. Right? So I'm just going to take those and plug them in to see what the function value is. I've got 8 edge critical points, right? That is, along each edge, there were some that looked like critical points. They're not really critical points for the function, but when restricted to the edge, they were local maxes and mins. There were places where the derivative with respect to one variable, anyway, was 0. And so there was 3, 5, minus 3, 5, 3, minus 5, blah, 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 the 5 2's, right? So there were 8 of those. And then there's 4 corner points, 5, 5, 5, minus 5, minus 5, 5, and minus 5, minus 5. So I'm going to take all of those, plug them into the function, and see what the function values are. Right? I don't need to do a second partials test here. I'm guaranteed that somewhere there's going to be a maximum and there's going to be a minimum because the square that I'm looking at is certainly finite in size, and I'm including the edges, so it's closed and bounded. So there's got to be a max and there's got to be a min. So I just look at all the function values, 70, 38, minus 38, minus 70. These two were our local maxes and mins from a previous video. Right? But then there's all these other things. On the edge, there's a minus 11 and a minus 119. Well, boy, that's pretty low. So along that edge, this was the local max and this was the local min. It turns out that this is the global min as well. But here's another point at 119, at 11, at 26, at minus 6, at 6, minus 26, minus 75, 75, minus 75. Sorry, minus 55 there, 55, right? So all of those were interesting points. I had critical points on the interior, I had sort of edge critical points, and then I had the corners, all of which might have the max or the min, and I got to check them all. So once you establish your only possibilities, then you can just plug them in and see which one gives you the highest value, the 119 right here, and the lowest value of the minus 119. And looking at the graph, it corresponded to this point as the minimum value and this point as the maximum value. I should point out that the scale looks funny because I'm saying this is a height of 116 and it looks like it's only about 4 or something. But in order to draw this graph, I scaled everything down by a factor of 40 because otherwise it would be really, really tall and not very wide. And so I just scaling it down, you still see the features as which one's the highest. It's just not as high as the function is telling you it's going to be just because I divided everything by 40. But as you can see, dealing with a boundary just gets kind of complicated. Now this one was 4 rectangles. Sorry, it was 1 rectangle, so the boundary was 4 line segments, and so I broke it up into working one line segment at a time. Maybe the region is a circle or an ellipse, in which case you would parameterize that curve, whatever the boundary is, and then you'd have that described as a function of t, right? One parameter. You'd have x as a function of t and y as a function of t, so that you would, in doing this evaluation, you would do f of plug in the x and y as functions of t, and then you would have this just as a function of one variable t, and you could take a derivative, right? There's lots of different ways of dealing with the edge, and the next topic in this course is what's called Lagrange multipliers, which is a really nice way of working with kind of any boundary as long as it's got a nice formula. If you've got an equation for it, then Lagrange multipliers is going to be able to handle that boundary. In the meantime, you got to work with it one variable at a time. Either plug in x as a function of y or y as a function of x, whatever it takes, or parameterize your boundary as a function of t, so you get it down to one variable, and you can do the sort of edge critical things by taking derivatives just with respect to one variable. Maxes and mins on a constrained region. Find what's going on the inside, check what's going on the boundary. You're guaranteed to have a biggest and a smallest, so take the biggest and the smallest function values as your global max and min.